Okay, so welcome. I see that we already have quite a large number of participants. Welcome to the networking channel. It gives me a great pleasure to welcome you all to this new edition, which is going to talk today about quantum networking. And quantum technology, as you know, has been around since quite some time. But we see that the interest is growing. Actually, we see more and more initiatives being developed and launched worldwide. We see also a larger number of startup companies. It's another indicator of the interest in this field. Large number of startup companies being funded. And we believe that there are more and more applications that might impact the networking domain. So for those reasons, I'm very pleased today to welcome three excellent colleagues that I'm happy to see in this occasion. So first, Frédéric Grosshans, who is Sorbonne University. Actually, he is in the same corridor as me, so I had the opportunity to stress him to organize this series, and I would like to thank him for that purpose. Frédéric is a researcher at CNRS in Paris, in the same lab as mine, LIP6 at Sorbonne University. He's specialized in quantum telecommunication with a background in physics, and notably, he is the co-inventor of the quantum key distribution technique. And he's the co-director of the Quantum Information Center at Sorbonne that has been established lately in Paris. Next, we have Don Towsley from the University of Massachusetts at Amherst. Don, it's a pleasure to see you here again. He spent a sabbatical with me at Sorbonne back in '91, so it's a long time ago. And I don't have really to introduce Don because he's certainly one of the leading researchers in the domain, and he has been since a few years now, entering also the area of quantum networking. So I'm very pleased that we have Don with us today. And last, Rodney von Meter is the one who raised awareness, at least for me, about quantum technology. I can say Rod quite a long time ago as well. And Rod is a professor of environment and information studies at Keio University, Shonan Fujisawa campus. He is the Vice Dean of the Graduate School of Media and Governance and the Vice Center Chair of the Keio Quantum Computing Center. And his research centers on quantum computer architecture and quantum networking, as well as many other topics. So before we move into this topic that we believe is of utmost interest for us, certainly with very important scientific questions, practical impact, potential PhD for doctorate candidates, I remind you that you can use the chat to submit questions. And we are going to stop on the hour. So if you want to continue the discussion, I would remind you that we also have the Slack channel, gently provided by SIGCOMM. And the program is recorded, as well as the presentation will be stored on the website. And you can replay the program on the YouTube channel. So this being said, again, thanks a lot for joining. Rod, sorry to take you awake at 1 a.m. in Tokyo. And I hand over to Frédéric for organizing the session.
Oh, thanks for the invitation. And I mean, the organizing of the session, we will start with Rod because, I mean, I think it's the best to introduce, and given that it's quite late for him, it's better to do it sooner. So Rod, the floor is yours.
Thanks. Yes, and Serge, it has been quite a while that we've known each other now. It's really nice to see you, and thank you all for the invitation to talk today. One small correction to Serge's introduction. I'm no longer Vice Dean of the Graduate School. My term as Vice Dean has ended. So currently I don't have a management hat to wear. So I'm just professor these days.
Lucky you.
Oh, except for, well, for the Keio Quantum Computing Center, I'm still vice chair of that, but for our campus, I no longer do. All right, so let me give you just a few minutes real quickly about some of the work that we're doing, and also hopefully a little bit of an overview of some of the general ideas behind quantum computing as we go as well. So I'm going to go through a fairly large number of slides fairly quickly so that we have as much time as possible for discussion. So here's a list of me and some of my collaborators. I've got 3 names highlighted there in bold, names that some of the organizers here will recognize. Frédéric Grosshans, who's graciously invited me to be involved in this, and our collaborator Damien Markham and Clément Mignon. So this is currently my group. Some of you will probably recognize the guy standing next to me there in the photo. While this photo is now 2.5 years old, thanks to COVID, we haven't all been in the same room and had an opportunity to take a good photo. But the group's now up to 28 people, so quite a large group at our campus alone, let alone the other Keio campuses. We also have the Keio Quantum Computing Center, which has grown and grown, and we now have, I think, 8 announced corporate partners in that, as well as a number of faculty and staff involved. So we've got quite a lot of effort going on in quantum computing. It's really an exciting time. Some of the research areas that my group is working on, we work on, excuse me, not only on quantum networks, which is the primary thing that I'm going to talk about today, but also on quantum computing, quantum education, and quantum community efforts as well. And so we have sort of a broad-based effort, but I consider those to be sort of the 4 pillars of what we're doing. So there are really 2 arms of what John Dowling has called the second quantum revolution, the first quantum revolution being the transistor and the laser. Quantum computing brings us advances in chemistry and material science, and hopefully finance and machine learning and optimization problems and things of that nature. And one of the areas that's often highlighted is cryptography, which in a certain sense, it advantages the attackers, and so it's considered to be potentially a destabilizing technology in that sense. But on the other hand, quantum communications has the potential to alter, in terms of for the defender, some of the things that are going on with communications security. And so there's sort of a give and take in that area. But quantum communications and quantum networking in the broader sense bring us additional capabilities, including work on high precision sensors and distributed computing. So I want you to understand that there's much more that's going on than just the efforts in the cat and mouse game in security. So I divide these applications for a quantum internet up into 3 major areas: the distributed cryptographic functions, sensor networks, and distributed computation. And there are a large number of applications that have been investigated. We're not going to have time to talk about these all in detail today, but feel free to ask us questions about any of these sorts of topics. And note that those security-related items, one of the things that we believe that they will do is they'll reduce our dependency on public key, cryptography, one-way functions, and computational complexity as some of the bases of security systems. So to realize a quantum internet, which will distribute quantum entanglement across a distance and allow us to achieve these different kinds of potential applications, of course, one of the things we're going to need is these applications that I just introduced very briefly there. We're going to need a lot of work on architecture and protocol design, which I'm sure are the kinds of areas where many of today's participants have a lot of expertise. And so part of what we're trying to do today is to recruit other people to join us in this effort to build a global quantum internet. And of course, one of the kinds of design tools that we want to have is we want to have simulation available, and we ultimately do it to have test beds and experiments. And then, of course, finally, profit, right? That's the standard Silicon Valley motive, right? Not that I'm in Silicon Valley, I'm currently in Japan. All right, let's see. So my group is working on at least 5 different major areas in terms of quantum networking. We're working on architecture. I pull out naming as an additional important and separate area. some areas in advanced networking, and then the two sort of ways of demonstrating what we're doing. We are working on physical test beds, and we're working on some simulation technologies, and I'll talk a little bit more about the simulation. In the architecture, we need all of the same kinds of things you need in a classical environment. We need the basic connection setup, you need routing, you need not only networking, but internetworking. You're going to need application APIs, and of course, you need multiplexing and resource management throughout the entire network system in some way, shape, or form. Naming involves not only addresses for the nodes themselves, and we have some specific ideas about how to go about doing that, but it also involves naming for the entangled states that are being developed, because in fact, the development of entangled states that are shared among multiple sets of nodes, the process of creating those entangled states is in fact a distributed computation, and the classical control plane for your entire network must exchange a lot of classical messages and discuss the development of those end-to-end entangled states that are being created. And so, of course, they're ephemeral resources. They are consumed during the process of executing applications, but you must be able to name them as well. We're working on a number of advanced technologies, including what are known as graph states, including multi-party states, which is in fact what we're working on with Fred, and also some advanced error correction-based architectures known as 2G architectures. In terms of our simulator, of course, there's a lot of additional simulation infrastructure that has to be developed, and we actually have plans that are in development that have been severely impacted by the course of COVID, but we're actually in the process of doing some work on test beds as well. Finally, at the other, at one end of the scale, you have modular interconnects that can be used within a single data center to connect quantum computers that are sitting next to each other. And at the other end of the scale, we have a map of the entire classical internet. How do you simulate something that's on that kind of scale? And so those are the kinds of issues that we're dealing with internally. So we have developed a system we call the Quantum Internet Simulation Package. It's an event-driven simulation of repeater networks. Those of you who've worked with Omnet++ have seen something like this before. It is rule set driven, so it's what we call the condition clause and the action clause, which are much like SDN's match and action clauses. And you have a physical setup that looks something like this, and we distribute rule sets to the different nodes in a distributed fashion that describe the set of actions that have to take place. Let me show you just for a couple of seconds here. This is what the simulator looks like in action. If you've worked with Omnet++ before, the UI will look very familiar because it builds very directly on top of that. A number of research questions, emergent behavior, how do we verify the protocols, can we predict performance, and one of the things that I'm very interested in, what happens as conditions inside the network change, things like that. And all the basic classical networking issues apply just as well on the quantum internet. So our goal with this is actually to simulate an entire network with up to 1 million qubits inside the system. That means that we can't actually execute a complete simulation of the whole thing. So we have to make a number of sort of compromises as we do it as we go. And we can talk about those if you like. The simulator itself has been released as open source. It's available on GitHub. So we very much encourage you to download it and try it and to join us in our efforts. And if you're interested, in fact, there's a WASM version of it that's available. All right, I want to make 3 quick plugs here, but as I wind up. We have an organization that's known as the Quantum Internet Task Force. We're building here in Japan. The goal of that group is to build an actual testbed network as we go. And I am currently co-chair of the Quantum Internet Research Group, which is part of the Internet Research Task Force. If you're interested in the topic, please do join us on the mailing list. There are about 400 people on the mailing list right now, I believe. And the traffic level is entirely manageable, so please join us if you're interested. And finally, I'm also an editor on the new IEEE transactions on quantum engineering, and we have a special section on the quantum internet. So please feel free to read those papers and join us by contributing. And with that, I'll hand it back to Fred. Thank you.
Thanks, Rod. So let me share my screen.
You have the same black box.
Yeah, I think I understand. No, it's just in a corner.
The big black is still there, Frédéric.
The big black is still there?
Yeah, the big one.
Oh. That's problematic then. Sorry, and let me try to. Now, if I do it this way. Is it?
No,
Still there.
Still there.
Oh.
Frédéric, if you want, I could go next while you see if you can fix it.
Yeah, I think okay.
Okay.
Thanks a lot.
Sure. Okay. So what I thought I would talk about is, I guess, my view of a quantum network, some of the challenges that I see us facing, what I think are some research opportunities coming out of, let's say, work that we've been doing at UMass, and then some conclusions. I'll be a little bit more technical than Rodney. So my view of a network is that it wants to generate and serve entanglement. You have a bunch of quantum switches. They're connected by lossy links. They host quantum memories. And then basically what happens, is that the links try to generate what are called bell pairs or entangled quantum state. And then the switches essentially try to concatenate them so that you have end-to-end entangled states between the users. And I sort of show it with this picture here. This is all probabilistic. There's a probability P that a link will succeed in getting a bell state, probability Q that the switch will succeed in being able to do the concatenation. And that's sort of important to keep in mind. And so here's sort of what I see as some of the networking challenges. One, there's a question about what architecture we should use. I described what's called an entanglement distribution architecture, but there is work on developing architectures where you would just directly transfer quantum information across the network. And that looks a lot more like a classical network than the entanglement distribution network. There are questions about resource allocation. Almost all of the work that's been done is essentially looking at the behavior for a pair of users, and we need to be able to share among multiple users. We have to figure out how to set up paths between end users, how to schedule the switches, how do we model performance, what should the data and control plane look like, how to do measurement and management. And I want to just talk a little bit about what we've been doing at UMass. For example, in the context of routing and path selection, suppose you have an Alice and a Bob in this 2D network. And as I said, the links are trying to establish bell pairs. And so let's say we have an instance where the edges in this network correspond to successfully generated bell pairs, and then switches will try to concatenate. And so in principle, Alice and Bob could end up with sort of like two end-to-end entanglements. And so there's a question of, how do you go about deciding, which bell pairs the switch should try to concatenate. And so we've looked at performance in terms of the rate as a function of distance between Alice and Bob. And what we see is one curve here is when they use global link state knowledge. That, of course, is not really tractable. So we've looked at algorithms that use local link state knowledge. And then I'm showing at the bottom what would happen if you just sort of dedicated one path between Alice and Bob. And we see that there's a benefit to using diversity. What's interesting is that all of these display sort of an exponential decay in the rate as Alice and Bob get farther apart. And so part of our work has been to try to get rid of this decay. And it turns out that by using more complicated, let's say, quantum states, what are referred to as GHZ states, you can. And essentially what you do here is instead of concatenating two, let's say, states across two links, you would concatenate 3 or 4 at the switch. And so whereas let's say in this setting right here, Alice and Bob have a path, but the wrong concatenations were done. Once you allow for these sort of more or richer set of concatenations, then you would establish a path. And what we've seen is that by building up these sort of 3 and 4, let's say, quantum states, you can get entanglement rates that are independent of the distance between the consumers, as long as the success probabilities are large enough. And that corresponds to these blue and green curves up here. The curves down here, the success probabilities aren't large enough, and so you get 0 rate. And it's interesting, it ties to percolation theory, which is something that I like. I'd like to say a little bit about scheduling in the switch. If you take a quantum switch, what you're doing, of course, is you're generating these bell pairs across the links, and then given outstanding requests for, let's say, end-to-end pairs, the switch has to decide which ones to concatenate. And it turns out that that's equivalent to selecting an eligible matching in a graph that's across the memories in the switch, which I've sort of shown down here on the right. And so the outcomes of these matchings form a set of end-to-end entanglements then between pairs of end nodes. And what's nice is for those of us coming from classical networking is you can adapt some of the rich set of switch scheduling policies to the quantum setting. And you can characterize what the maximum capacity region is as a function of sort of the amount of memories you have in the switch. It should come as no surprise. Max weight scheduling is optimal in this case. And you even have opportunities of storing bell pairs at end nodes, even though there are no requests. And so you can get low to 0 latency. Now, max weight scheduling is computationally very expensive. And so there's a really interesting questions about, what are good lightweight policies? How do you extend to network setting? And so the issues that come up here then, have to do with what's the performance. the benefits of global versus local versus no state information, the time scale at which you might want to exchange state information. It should come as no surprise. It should be possible to borrow ideas from circuit switching and classical networking. I've ignored what's called decoherence, that namely the quality of quantum information degrades over time. And it turns out that when you start to consider that, then policies like last in, first out make more sense than first in, first out. There are opportunities. You could have, let's say, a capability of generating, storing bell pairs, and then serve them as needed. And so there's some similarities to the future power grid that might make for some sort of synergistic research opportunities. Just one last thing, having to do with control plane. I think that people are sort of the opinion that you'll have a quantum data plane, classical control plane. There's a lot of work on extending software-defined networking to accommodate quantum. But it's interesting to ask, could you have some kind of a quantum control plane? And we've been doing some work at UMass where we have a control protocol that in quantum parlance is really a sequence of unitary operations corresponding to what's called a quantum walk, which can be used to propagate control through the network. And it consists of, there are two operations. One's called the coin operation. You can think of it, it's sort of selecting the next node to sort of propagate the control information to, and then a shift operation, which actually does propagation. And because it's quantum, you don't have to specify one specific node to send to. You can sort of spread it across the network, sort of in parallel. And it can be applied to, let's say, entanglement distribution to distribute the quantum computation. So summary, I think the architecture where you're going to have entanglement distribution service, it's very different from the data transfer service. And I like it because of the difference. And so it introduces sort of new problems, and it introduces old problems, but with new wrinkles. And there's just lots of opportunity in terms of like performance modeling, doing resource allocation, how to distribute, manage entanglement state in very noisy environments, what the right control architecture is, how to do network management. And for those of you who are thinking about this, the research in this area is really in its infancy with lots of exciting problems. And I'll stop here. Thanks.
Excellent. So it was easier to ask Frédéric to join me in my office to start with. We have been using teleportation instead of quantum communication. This is it, and I will leave the floor to Frédéric.
Okay, so thanks, Serge. And thanks, Don and Rodney for your introduction. So now I will present the kind of quantum network research we do here in Leipzig, in Sorbonne Université in Paris. So I'm obviously not, so how do you, okay, sorry. So I'm obviously not alone in this team. So in our team, we have 5 PIs. Eleni Diamanti, Elham Kashefi, Damian Markham, Alex Bredayel, Ruilo, and myself, and as well as many postdocs and PhD students. One of the big interests we have is that we look at many different subjects, a bit like Rodney's team, from quantum computing to quantum cryptography. But what is interesting in quantum network is that basically we have, okay, no, sorry, I'm a bit too fast, but we have very different backgrounds and work well together. I mean, from experimental physics to pure complexity theory, and all have application in quantum networks. So we have a kind of vision of what would be quantum classical networks in, let's say, medium term. I mean, some of you know, currently they are very limited, but in the long term, given the price of quantum computer, which is currently infinite, they won't look like current, let's say the current internet, where in every node you have a fully working computer somehow. I mean, embedded hardware is slightly less powerful than a supercomputer, but it's nothing compared to the difference between a quantum computer and a classical processor. So in the long term, a network, you will have a few big and expensive quantum devices, mainly quantum computers, but you could also have quantum simulators, many small quantum devices which will do elementary operation. I mean, an example of such quantum device we expect to have is the quantum switch Don introduced, and which can help a lot. And of course, many, many more classical devices. I mean, you all listening to this talk through a fully classical device, and they're way less expensive than even a quite cheap quantum key distribution setup now. So it will be somehow our free resource. And between all those devices will be connected with quantum channels, but also classical channels. I mean, what I call classical channel can be an internet link, or, I mean, being a theoretician, I don't really make the difference between a 19th century telegraph link and a fiber optical link, unless I want to watch Netflix, but that's another question. But so we need to deal with all that heterogeneity, and there are interesting stuff to do at each level. And basically all that, we look at it in a full stack. I mean, what I like to call full stack, or we have the whole quantum network stack. I put stack here in scare code because the networking stack for quantum has to be defined. I mean, several colleagues would beg to differ because they have redefined it, taking inspiration from the classical network, but they don't agree with each other. And I know that in classical networking, the exact definition on the various layers of the stack is is not exact, and people don't exactly agree. But for the quantum networks, it's even, I mean, worse or more interesting in the sense that everything is to be defined. So here I use the term in the sense that basically we go down to the hardware and really designing the hardware with theoretical quantum optics and experimental quantum optics done, for example, done by Eleni, which is experimentalist on our group, but does some theory too. Then there is a part which would be familiar to much of the audience, which I call network management, probably a bad term, but which includes the routing, scheduling, and all that, and quantum resource distribution. And it's something which I end up to be only recently interested in. I mean, I have a physics background and not a computer science background. So, but after discussing with many networking colleagues, including, I mean, you remember a meeting with Rodney or with other networking colleagues who say that when I was speaking of a protocol, they were saying, but that is not a protocol, because I'm not used, or I was not used to define something with all the details what internet protocol is. And it has important effects. I mean, in most of my theoretical work, I assume classical communication between any two people is totally free, and which is of course not the case. And on top of that, we have a stage which I call toolbox, or we have a primitive, when we have lots of what I usually call protocols, where basically all the group meets. And I mean, that can be many cryptographic protocols. The most known of it is quantum key distribution, secret sharing, secure multi-party computation, problem of remote state preparation, a lot of stuff. I mean, basically, it's a lot of the theoretician's problem. They say that the classical networking equivalent, you say, oh, I want to share a qubit with you. And it's really primitive operations, which are not really useful. I don't really, in an idealized setup, but it sits in the middle, but it's really interesting. And then on the top layer, you have the application, which is most of the realm of Elham Kashefi here, where you use the previous stuff to build more elaborate protocol, actual use cases, and so on. And all that, I mean, some of them is really application which assume, let's say, today technology, your QKD setup. I mean, when I say today technology which is available today in the lab, and okay, and some of them even commercial, but really expensive. I mean, it's not the same kind of today technology as my phone or whatever, but it's still with relatively low TRL, to technology which suppose that basically you need a full quantum computer connected to a network. And on top of that, I mean, maybe because one of the first application of quantum networks is cryptography, we have a strong cryptographic point of view. And then we need to check that everything is correct. And so there is and the big specialty of many Elham is also the verification step. How to check that, for example, the GH set on Towsley to use in the network are actually GH set. And depending on your setup, you can say either you trust your network and you just want to evaluate it, it's just against noise, or you don't trust anyone because you want to use that in a cryptographic scenario and you want to be sure that the network is not spying on you. To take some examples, so I will now go a bit quickly to some more concrete example. I mean, going back to the bottom of the stack at the hardware. At the hardware level, the first step is the optical system. So there is one part which is more my work. I'm a theoretician, and it's designing optical system, but in a kind of idealized way here. I mean, here is an example on how to improve band measurement, which is a key element of teleportation with some limited resource. Some stuff we are working on is, for example, photonic error correcting codes to diminish the problem of losses in quantum network and this kind of stuff. So my point is basically on an abstract level, on a theoretical level, and Eleni Diamante does actually, I mean, I didn't have a picture of their setup, her setups, but actually builds quantum key distribution setup and more elaborate setup. And here you see a depiction of a network we are building in the Paris area between where the center is here at Sorbonne Université with other place, I mean, our colleagues of Université Paris, I mean, inside Paris and other place around Paris. And this will be an optic, some links are already here and it will be connected through QKD. And it's a way also to test how the protocol we design in the abstract are actually useful, I mean, usable in reality. And there is also big problems, usually big problems that happens in this kind of reality check, hopefully not here. And also, I mean, the big work is, I mean, I speak of the network aspect, but Eleni also works a lot to improve the performance of individual links, for example. So currently, this will be a QKD network. So for people not familiar, quantum key distribution, somehow the link itself is quantum, but because of the quantum nature of quantum information, we are not allowed to have repeaters with current technologies. I mean, ideally in the long term, we would need to have a quantum switch than the one Don Towsley presented, but then they are challenging to build, to say the least. I mean, there are some works, I mean, there are many works in many labs, including in the physics lab of the current university. So one hope is then later to replace those nodes with quantum and to have a few quantum repeaters and have a full quantum networks. Another work, I mean, as you see, the scale here is quite limited. I mean, it's a few tens of kilometers, but if you don't have a quantum repeaters, and if you don't trust the node, you can't go much further. I mean, you can go a few hundred kilometers, but not much more. And there is a solution which we look actively at, is the use of satellite as a relay. So here is a project we have with the University of Nice, and also managed by LNE, so to use the satellite to relay key and so on. I mean, currently there have been experiments with satellite, and the group of Zhang Weipen in China is the only one, to my knowledge, who have done quantum key distribution in satellite, and they have project to bridge various parts of the Chinese QKD network through satellites. But they're not the only one working on it, even if they're the only one to have a satellite. And so we study, of course, satellite links are really different from fiber links, and the problem you have to look at, like turbulence and so on, are different. And then you have a bunch of data when the satellite goes in front of you, or you put your satellite much further away in geostationary orbits, and it changes a lot of stuff. So here you see curves to try to check the rates, the key rate you could get in a continuous variable QKD setup. And the idea would be to bridge, it's part of a European project, and the idea would be to bridge several local, let's say, metro area networks through satellite. So another aspect, a bit higher in the layer, and immediately it becomes more abstract. It's the work I did, for example, with Damien Markham and Clément, and which is what on the network management, or I mean, if you look at all paper on quantum networks, the networks is already only a line. And here we looked at how to distribute multipartite state in a slightly improved version of a quantum switch, where you allowed different stuff and to create GHZ state. Don't spoke about, but I see I'm running low on time and probably we have questions. So, and that, I mean, this is a quite of abstract work where, and we also did another kind of work when we look at what kind of tasks are actually possible with the quantum version of network codings. But the more concrete work we have started to do with Rod is how to actually deal with those abstract protocol and simulate them in QUISP. And at the moment when we see that we really need to deal with the classical network aspect of the stuff. And another thing is that those networks don't work like a message which go across, and then how to deal with congestion. That's when you have several people, several sets of clients who want to communicate simultaneously. And we are starting to discuss with, colleagues in the same group as Serge, and trying to adapt the, usual classical network problematics to strategy to that. Then on the toolbox, these pictures, it's really lots of cryptographic tasks you can do. To give just a single example, because I'm running low on time, and which is the one of this picture which is taken from a PhD student of Hilham, a work we did together, is one of the questions might be, okay, there is a quantum computer on the network, and all other players have really limited quantum resource. And if we combine that with a part of cryptography, which is called post-quantum cryptography, we showed that we could use the network to the quantum computer to do a totally anonymous routing, where no one, even the computers who actively does the routing, can guess who is connected to whom through the distribution of GHZ states. And it's a kind of a limit of work that is, if you have a big quantum computer, it will be really expensive, but it can be how to use it, even if you have only really limited resource, or maybe only classical resource. And it can be really at the heart of the network routing. And then, okay, I end with that, and a quite example of application is something developed by Helham, which is a quantum protocol zoo, which you can Google, and which try to record all kind of protocols on which kind of primitive they need. So to go, either I want to do this kind of quantum signature, then what are the hardware you need, or the other way away, to try to find the useful applications. And okay, other applications that are blind quantum computing, so where you ask a quantum computer you don't trust to do a computation for you, or use it directly in also in the more realistic stuff, in the sense that when you have limited hardware, it's probably possible to use a network to distribute a quantum resource across several places to make quantum measurement, to improve the precision of measurement. So it's a more abstract kind of network. Maybe with the sensor might be really close, but this kind of minimal network need to keep entanglement to keep good measuring quality there. So thanks for your attention, and I think now it's time for the questions.
Yeah, thank you again, Frédéric. Let's move into the question now. I see that we have quite a few questions that are popping up here and there. So there is one question, and I will leave maybe Frédéric hand over to whoever. So there is one question.
No, you can.
There is one question for dealing with. So quantum memory is an integral part of repeaters and networks. Could the panelists comment on the state of the art in quantum memory devices? So practical technological question. Who would like to take this one?
I can make a couple of quick comments. So there are many different hardware technologies that are being developed for quantum computing. And you're correct that different ones have different memory lifetimes. And of course, when we're talking about potentially intercontinental latencies of hundreds of milliseconds, those lifetimes are important. The most famous quantum computers these days are probably the superconducting computers of people like IBM, Google, and Rigetti, and they have lifetimes on the order of 100 microseconds or something, so it's not very long. They've got a bigger problem, which is how do you translate the information in the superconducting circuit to photons that can be used for the communications. A couple of other technologies that are very that are well suited to communications are ion traps and NV diamond, and they both have much longer lifetimes. The ion trap folks claim that they can keep a state almost indefinitely, depending various reports, of state lifetimes of up to as much as an hour for ion trap, but more realistically, somewhere in the sub 1 second range. But the memory lifetimes there are probably not going to be the problem. It's going to be more a matter of the fidelity of the actual operations that are used, and dealing with the fact that the individual atoms like to emit at particular wavelengths that are not as well suited for transmission in fiber as some others. So it's a big issue, but it's also one that's tied very much to the particular technology that's in use. Delft has probably the most advanced physical networking implementation, and they use the NV Diamond platform. And for them, I don't think memory is really the limiting factor in their current protocol. It's really the low success probability in generating the entanglement for each individual trial, and therefore the protocols that work around that particular issue, and then sort of the middling fidelity of the individual operations.
I'll just say that the MIT, Harvard network activities are also following the same technology as Delft.
Excellent, thank you. I'll move to the next one and take the opportunity to say hi to David Oran. He has a question here. I was curious about the term quantum network coding. It is colloquial or specifically applying what we today understand as network coding? namely linear combination of multiple inputs to improve robustness to quantum channels.
So
Ooh.
it's
Yeah, go ahead.
it's not colloquial. It's related. I'm not exactly sure that it's what you. I mean, it's related to something we understood as a network coding as used in the classical network setting. I'm not sure it's exactly to improve robustness, but I mean, the classical example is a butterfly network where you cannot in a one shot route 2 bits in a crossway. Why? Because I should use the same link while using a function of the various inputs coding the various input bits, and you can find a way, each node making a XOR of the various qubits. So it's really linked to that in the sense that instead of just moving your bits or qubits from one place to the other, you can make more elaborate processing of it, such that what you intermediate nodes, I mean, intermediate link, don't exactly contain the inputs, but you can decode at the output. So yes, there is a strong analogy, and it was building on a work by François Le Gall in Kyoto, I think. I forgot in which university he is in Japan.
He's currently at University of Nagoya University.
Okay.
Yes, and the Francois' work, some of that work was done with a guy named Takahiko Sato, who was a PhD student at the University of Tokyo when Francois was there. And Sato was my undergrad and is now back in my group as a postdoc. And so he's published several papers on the topic. I posted a link to our publications. You can find them there.
And so that work said that if you had a classical network coding, then you could have a quantum network coding from the same problem, which was really following the track. And the question was whether the converse was true. And by linking the problem to a problem of factorization of tensors in either the complex field or the positive reals, we could show and give a counterexample where there are examples when we have quantum network coding and not classical ones.
Yeah, no further comment on this? No. Okay, so there is another question, which is targeting Don. Can you elaborate on the similarities between the future electrical grid and quantum networks?
Your mic is off, Don.
Yeah.
Sorry, I thought I had unmuted. What I was referring to, it looks like we're going to an electrical grid where we're going to be using renewable resources that are sometimes going to be generating electricity when we don't need it. And so eventually we're going to probably have huge storage units for electricity. And as Rodney mentioned, there are memory technologies where the qubits can stay around for minutes, maybe hours. And so what I'm referring to is I could imagine there being essentially a set of storage devices that when nobody is consuming entanglement, that you would generate it, just put it into the storage devices and then serve it when requests come in.
There is one further question, which is the energy be a key issue to reach the quantum internet?
Indirectly, yes. I mean, directly, our key issue is not energy costs. I mean, all the problem is really doing good quantum memory, having precise operation, fighting decoherence, and so on. However, most of this, there is a link. I mean, you have a stronger link with energy in quantum computers, in the sense that the quantum computers are reversible computers. So in theory, there is no lower energetic cost for their computations. And if your small, if your local operation you do in your small processor on the networks leaks energy, it leaks information and makes decohere. So there is a link to that. But then there are questions whether it will cost in the total more or less in the very long term than the internet, the current internet. But it's just, I think it's really an open question in the very long term, and it won't be a problem over the next decades, so to say.
So maybe a last one, because of our time constraints. How do you see, or how do you use this for sensor networks?
So yes, it's a. I mean, it's not a network of independent sensors. Is sensors who share. I mean, depend what you probe, but. Actually, it's not my specialty, quantum metrology.
It's hand over to Don or Rod if you have an idea.
Well, I'll give my naive answer. Again, this is not my specialty. As Frédéric said, it's you have a set of sensors that are sort of observing sort of the same thing, and they're trying to, let's say, estimate a parameter associated with this process. And it has been shown that if you share entanglement between the sensors, that it can be taken advantage of to get sort of higher resolution readings, particularly when the signal to noise ratio is very, very low. It's not particularly useful when signal to noise ratio is high. And so that means there are some applications where you're just better off getting classical sensors and putting more energy into it. I have the sense that maybe it's going to be useful for things like deep space, let's say, exploration from observatories scattered around the country.
But also at another scale.
Yeah. Sorry, just one comment on the sensor networks. So the one way to think about an entire class of uses for distributed entanglement is to treat them as a physical reference frame. And that makes it particularly useful for things like physical synchronization of clocks. And so there have been several proposals to use distributed entanglement for high precision clock synchronization, for example, which is ultimately related to things like the use of distributed entanglement for improving interferometry for very long baseline telescopes, for example.
Okay, thanks a lot. We have been discussing this since an hour. And again, I'm sure that this has raised more curiosity, interest, and excitement about this topic. And I'm sure that many will certainly consider looking at some of the papers of the topic that have been discussed here. So I would like first to thank the speakers. Of course, Rod, thanks for staying very late at night. And thanks to Don and Frédéric for their commitment to organize this session with us. And I would like to close by reminding everyone that, of course, you can replay the program on our YouTube channel. And if you have further questions, they're most welcome on the Slack channel. And I'm sure that our speakers will take a look at them. And last, just to remind you that the networking channel is playing every second week, exactly at the same time for an hour. And the next program will be about human-centered networking with a presentation from Hélène Zegura from Georgia Tech. And the chair, I'll be very happy to hand over to Jim for that. Thanks a lot for your time. And again, looking forward to meeting you on the networking channel in 2 weeks from now. Have a nice morning, afternoon, day, night, and take care of you. Bye-bye.
Stay safe, everybody.
Bye.
Bye-bye.
Thanks a lot.